Okay. It's 4, so I'm gonna get started. I have to leave at 4:55 today because I actually need to return the Mac adapter that I borrowed from someone else. But I actually planned for this to take about 55 minutes to begin with, so hopefully it'll all work out in the end. Yeah, so I'll be over here. Hopefully you know this is a discussion session for testing. The plan for today is to write a little bit of code and see how I write that, and how I also write tests while I'm writing the code to make sure that it's working correctly. Okay, I'm going to SSH into my account. You don't have to do that if you don't want to, if you're on your laptop right now. But if you don't, then you'll only be able to code along with me for the first 30 minutes or so, because after that, I'm going to be doing some stuff using one of the libraries that's installed on the lab machines. So it's going to assume that that thing is already installed. So yeah, if you're not really comfortable with using Vim or Nano or something like that, then you can code on your own machine. But if you want to follow along for the entire time, then you'll have to SSH along with me. I'm just going to choose the machine, hopefully it stays up. Can all of you see this clearly? Okay. Alright. The motivating example that I have in mind for today is a binary search. I'll just make a directory for all the code that we'll be writing. And we'll cd into there. We'll see right now that it's empty. And we'll put in a file, binary search.cpp. Here you go. Yeah, if you're not comfortable with using Vim and you're following on the CSL machines, then you can use Nano instead. That's another text editor that's entirely on the command line, but it's a little bit easier to use. I'll try not to do too much Vim syntax magic when I'm explaining stuff today. Okay, I'll just write the main function to get started with. And the prototype for our binary search. And since we're going to be using vector, we're going to have to say pound include vector. And over here, for now, we'll just say we'll return 0. I just want to make sure that this basic piece of code at least compiles. We're going to be printing stuff out too, so I might as well do this now. We'll say pound include IOStream. So yeah, just a little bit of code to get started, nothing too unusual yet. Okay, I'm going to save and quit. If you're in Vim, that's :WQ in normal mode where you can enter commands. And then just hit enter. It should bring me back here. And we'll see that the new file that we created is already here. Okay, I'm going to compile it. Okay, it looks like it compiled. And if I run it, then nothing's really going to happen, because we haven't really implemented any of the methods yet. Okay, I'll write a very simple implementation of binary search. Basically, what binary search does is it takes a vector and it looks for the position of an element in the vector. It assumes the vector is sorted, and it looks for where key occurs in the vector. If it finds something, then it returns the index where that element is. If it doesn't find something, then it returns -1. Okay, I'll get back to that. When we're doing binary search, we want to keep iterating over the entire vector, except on the next iteration, we're going to be looking at only half of the vector rather than the entire thing. Then on the iteration after that, we're only going to be looking at a quarter of the vector and so on. Basically, on each iteration of the loop, we're going to be reducing the size of the search space by a factor of 2. And because we keep changing the values that we're considering as we're narrowing down to wherever the desired element is, we need to keep track of 2 different integers that just represent the indices of the sub-vector that we're looking at, essentially, the sub-range in our vector. And we'll call those low, which starts out as 0, and a high, which starts out as the index of the last element in the vector. Since the vector is sorted, we know that if we look at the midpoint between those 2 different indices, which I'll just calculate like this. We're going to take a look at the element that's stored at that index, at mid, inside the vector, which is the midpoint between low and high. If the element at mid is less than p, the element that we're looking for, then we'll say, okay, we'll go to the sub-range on the right-hand side of mid. And then we'll keep looking at that sub-range on the next iteration. So, hold on, I may have said that wrong. If mid is less than what we're looking for, yeah, then we look at the right sub-range. If mid is greater than the element p that we're looking for, then on the next iteration, we look at the left sub-range. And if mid is exactly if element at mid is exactly what we're looking for, then we can just return that. Then we can return mid because that's the index that we wanted. That should be -1. Okay, so right now what we have, if what I explained earlier didn't really make sense, hopefully looking at the code explains things a little bit better. Essentially, for the next iteration, we change either the low value or the high value to determine what's the next subrange of the vector that we're going to be narrowing down to. And eventually, hopefully, we reach this case over here, where in the array, at that index mid that we've been using, we actually have the value we're looking for. Then we can just return that index. Just a couple of small changes that I'm going to make. This should be mid plus 1, because we don't want to keep looking at the element at mid after we've already considered it. And this one over here is actually pretty similar. Okay, let's check if it compiles. And again, when we run it, if it does compile, it's not going to do anything yet. Okay, it compiled. And then if we try to run, nothing's happening because we're not calling the binary search function, at least not yet. Okay, let's go back here. Now that the binary search function is more or less done, we can start writing a couple of test cases to make sure it works correctly. If we can think of some test cases, like some inputs to the function, that cause it to return the wrong value, then we can fix that, then we can fix the function itself. So for the time being, I'm just going to say, inside main, let's create a vector. And we'll add a couple of elements to it. Okay. I just created a vector that has 4 elements, 5, 10, 15, and 20. And I also called the binary search function by passing in that vector and also the index 10. What we're expecting when we run this is it compiles and then it prints out the value 1. The reason for that is because the element 10 is located at index 1. Like 5 is at index 0, 10 is at index 1, and so on. So this is just one basic sanity check for binary search to make sure our function is working correctly. Okay, I'm going to, again, save and quit out of Vim. I'm going to compile, and now I'm going to run. We should expect the output 1 on its own line in the output. So yeah, we see the number 1. I'll move it up here. Which means our program is at least sort of working correctly. We need to come up with a couple more edge cases to make sure that it's actually working correctly in all cases. So far we just printed out 1 value, but what if we look for a different element while performing binary search? So let's look for an element that's somewhere in the middle of that vector, but isn't actually, or is between 2 elements in the vector, but that element itself is not in the vector. We're expecting it to return -1. That's what I explained earlier. And let's see if that happens. Compile and run. It looks like what's going on right now is it printed out 1, and the program is still going. I think some of you might know why this is happening, but does anyone want to take a stab at it? Yeah. So whenever the program just keeps going on and on like this, it usually means there's an infinite loop. Which makes sense actually, if you look at our code. We're saying while true. And there's no break or anything inside there, which means it could just keep looping on forever. So we know from the first line over here, line 27, if we search for 10, that works fine. So our binary search seems to work well if the element is in the vector, but we know from the second line over here that it doesn't seem to work if the element is not on the vector, because of this infinite loop over here. Okay. So we need this loop to end at some point. It turns out that the way it ends is if low and high keep changing, they keep getting narrower and narrower, and zooming in on some area in some subrange in the vector. And eventually, they'll narrow down so much that they'll actually just be equal to each other. Because we're performing integer division on them, or sorry. We're performing integer division, we're computing the average of the two. Which means we're never going to get a decimal value, which means eventually these two things will actually just be the same. So if low is less than or equal to high, then we keep performing iterations. If not, if they're equal or if they've if they're equal or if they've passed each other, then we have to break out of the loop and then go to the line at the bottom that says return -1. Just to make sure this works correctly, like, it's easy to say these things. It's easy to say, oh yeah, that makes sense. Like, logically speaking, that makes sense. But more than anything else, it's good to just run this code and just make sure that our logic doesn't contain any errors. Okay, so now we see the 2 lines. We see 1 from the first basic test case that we wrote for 10, for the element 10. And then we see -1 for the element 13, which means it's not in the vector. So we can come up with even more test cases like this. We can just look inside the array, inside the vector, for different elements. We can try looking for, let's say, the last element in the vector. Similarly, we can look for the first element in the vector. Yeah, it's good to check these two cases because in general, whenever you write code, it's easy to write code that works for basically things that are in the middle of whatever you're dealing with. But then it might fail for the two streams, which in this case are just the first element and the last element. So this is a good sanity check as well. Okay, let's see what's going on. Okay, we got -1. I think I made a typo. I think I typed in 0 when I was writing that line. Okay, but that's actually right anyways. So 0 is not in the vector. 10 was in the vector, we saw that. 13 was not in the vector, we saw that. And 20 is in the vector. It's the last element which had index 3. Yeah, that's what I wanted. I mean, I'm pretty sure it's going to work. Actually, no, it's going to work because they wrote all this code out already. Okay, there we go. I just added 2 more tests. Okay. 0 is not in the vector. 5 is in the vector at index 0. 10 is in the vector at index 1. 13 is not in the vector. 20 is in the vector at index 3. And 25 is not in the vector. All these look right. All right. We can add a couple more test cases just to make sure this works correctly for different vectors that contain different elements. But before we do that, I'm going to make a couple of changes to this code right here. So if we are planning to write more test cases with different vectors, it's going to get a little bit annoying to have to look at the screen each time to check that these values are correct. Right? It's already getting a little bit difficult. You have to go through each of those 6 different values and remember, okay, what did we write in our code? Oh yeah, that one was element 0. Yeah, we printed out -1, that looks good. So if we keep adding more test cases, just like more print statements like this, it's going to become really annoying pretty quickly. So it might be better to add something like, if the value is not equal to whatever it's supposed to be, then print out an error message. Then we can actually see the error messages that get printed. So essentially something like this. Well, actually, since we're already doing it 6 times, I'm just going to write a helper function to do this for us. So I'm going to write a function, expect equal, that takes in 2 integers, and then says, if they're not equal to each other, then print something. I'll fill that in a second, but I just want to explain what's going on here. The plan is, we'll use this function to check whether the output of a binary search function, whatever we call it, is equal to some other integer. And if it's not, then it'll hit that error message over there. And since it's an error message, I'm going to print a C error instead of C out. So we can change all of these lines now. Essentially, this line is going to become something like this. Expect equal that thing. And that one was supposed to be -1. I'm going to change this one as well. When we call that thing, we're expecting the result to be 0. When we call this one, we're we're expecting the result to be 2, or 1, sorry. And just so on, we're going to change all of these. I'm putting a typo in one of these on purpose, just so we can see that it actually fails when we want it to. So we're kind of testing right now that our test scheme actually works correctly, which is a little bit weird, but it's also pretty useful when you're writing tests. I'm just going to put error in all caps for now. We'll fix that in a second. Compiled and ran, and we see there's an error somewhere. So I know there's an error because I put one at line 38. The output should be -1, not 4, when we call binary search. So basically we know that the error message got printed. It might be useful to have a better error message. It might be better to say something like N1, the result when we call binary search gave us some value, which is wrong. Instead, the value should have been N2, which is what was expected. And I'll choose this error message very carefully. N2. This line's getting a little bit long, so we'll just put it there. So yeah, there is our new error message. Actual value is N1, expected N2. So does that make sense? Does it make sense what we're doing here? Why we're printing this error message, and also why it's useful to have all these different calls to expect equal to make sure that binary search is working right. Okay. If there are no questions, I'll do this one more time. Alright, we got no output, which is good. That's actually what we want right now. Okay, I still want to write a couple more test cases for this binary search function. Things like, if the vector is empty, then do all searches inside that vector, do all binary searches always return -1? Things like that. Some other edge cases that are related not just to the elements that are in, or like not just to the elements that we're searching for, but also the elements that are in the vector itself. Since this is going to become, since our main function is probably going to become really long, if we just keep adding to it, I think it's time to split it up into a couple of helper functions. So we'll have some test functions now. And we'll take our code from main and put it inside there. I don't want to type all of this again, so I'm just going to do a little bit of Vim magic. If you're using Vim, I'm going to explain it very clearly, and if you don't follow along, then please ask me for help. Okay, right now, I am in insert mode. I'm going to hit escape to go into normal mode, and I want to highlight all these different lines. So the way to do that is Shift V. It'll show that symbol over there. Basically, the whole line is highlighted. Now you can just use the arrow keys to go down or up, basically. You can select which lines are highlighted. We want to go down to here. These are all the lines that we want to cut and paste. And to cut in Vim, it's D. I'm going to go up again, a couple of lines. Right here to the first line of the function, and everything is going to get pasted after this. The way to paste is by pressing P. Okay. If you're all using, or if people are using Vim, I hope that worked. And I'm just going to keep going now. So there's our new helper function. Let's call it. And yeah, that's what we have right now. We can write a couple of other functions as well. So the example that I just mentioned was an empty vector. I'm trying to give these somewhat descriptive names. We'll get back to that in a second. Okay, inside main we're making sure that we're calling that function. And now let's add our code. It's going to be kind of similar to the last one, except the vector is empty. We're not going to call pushback on it at all. And essentially, we expect any binary search over that vector to always return -1. So we're just going to look up some element and say, okay, that should be -1. All right, everything looks pretty good up here. I'm going to save and quit. Compile and run. And it looks like both of those, like all of those test cases are still passing. All right. I can think of one more edge case that might cause some problems, which is a vector that contains just one element. And I'll put that test case over here. I'll call that a small vector test. We'll create a vector, we'll push back one element. And now when we're searching inside of here, it makes sense to have 3 different tests. One of them is any element that's less than 5. The next one is any element that's equal to 5, and then the third one is any element that's greater than 5. We're going to make 3 different calls, and we're going to make sure that they're all correct. And that's going to be -1. Okay, those are 3 function calls, 0, 5, and 10. I'm going to save and quit again. It's going a little bit slow. Okay, and wait, I didn't call the function like that. So we have to remember to call each of the functions that we write. That's kind of a bug in the framework, but that's what we're stuck with. This is what happens when you try to write your own framework from scratch. Okay, those are our 3 functions. We're calling them now. All right, we got an error message. Actual value is 0, expected a 1. We know it's in this function here. This is the one that we just added. And again, there's a typo right here, which I'm just going to fix. This should actually be 0. That was a bug in our test case itself. Okay, no, but once again, we're good. Okay, I think in terms of test coverage for the binary search function, we're pretty good for now. What I want to focus on next, which I already alluded to a couple of minutes ago, is problems with this rudimentary testing framework itself. Danny, do you see any problems with it? The way that we're writing tests and the way that we're calling them. Okay, I'll start us off with one. One thing is that down here in main, after we define the tests, we have to make sure that we remember to call them. We already ran into this problem, which was actually my own fault. Okay, another problem which isn't extremely relevant here, but it could arise in other situations, is if you want to use this test framework and you want to check, let's say, two strings are equal. Then what we have to do? This one over here wouldn't really work. Because expect equal is expecting two to... It only works if the arguments are both integers. So we'd have to write another version of expect equal that works for strings. And then that itself brings up a couple of other issues. Like when we're comparing strings, do we want to make it case sensitive? They have to match exactly, or case insensitive. A capital A is equal to lowercase a, and then those would be considered the same thing. So we can see this if we just keep adding other types, we add custom types, classes and such, and it starts getting really complicated. The other issue that I was able to think of beforehand is line information. If a test fails right now, it doesn't print out the line number. It just says, oh, a test failed. Like, expected value is whatever, expected something else. And there is a way to get around that in C++. There's actually a way to get the line number of the current thing that you're running, which line you're on in the program. But that's a little bit complicated and I don't really want to use it over here. Basically, the point I'm making is that once we start trying to add all these nice new features to this rudimentary testing framework, it kind of starts getting messy and starts breaking down. The good news, though, is other people have already run into this problem, and they've come up with solutions for it. So yeah, in general, if you're working in companies, or if you're doing research or something, people want to write tests for their code. Well, not necessarily, but good programmers want to write tests for their code to make sure that things are working correctly. And if something breaks, then they want to see where it broke, and then send someone to fix it. And since so many people have run into this before, there are lots of different frameworks that you can use to actually write these tests. And they avoid a lot of the problems that we already discussed. Yeah, the testing frameworks differ slightly from language to language. Like, depending on how much Java experience all of you have, you may have used stuff like Ant or JUnit to write tests. In Python, there's also one that's built into the standard library, which is actually really nice. And in C++, we're a little bit limited, but luckily Google decided to come up with a testing framework, and it's Google, so I'm going to trust them. Their framework, they decided to name it after themselves. It's called Google Test. And I'm going to be spending the next several minutes explaining that. Okay. Let's actually look at the docs for Google Test. So this is their main page. Yeah, their code is open source, it's on GitHub. It says, welcome to Google Test, Google C++ test framework. There's a lot of information that doesn't really help us. This file is important, the README. This is going to tell us how to basically install Google Test. I'm actually going to skip this for now because Google Test is already installed. I made sure of that on the lab machines. But if you're interested, if you want to write your own tests, like for your project or something, then make sure to read the README, because that'll tell you how to get started. Let's see. Somewhere over here, it should have a link to more information. I'm just trying to remember where it is. Yeah, here it is. So getting started information for Google Test is available in the Google Test Primer documentation. Let's take a look at this one really quick. Again, I'm going to skip the first couple of paragraphs in the intro. If you're interested, then please read this. It has a lot of really useful information just about the philosophy of testing. Setting up a test project, I'm going to skip that too. And basic concepts, I'm going to skip that too. This is what I'm really interested in. Writing assertions. So this is what Google Test looks like when you're writing tests, like writing individual lines of code to test your functions. You can say something like assert EQ, two different things, or expect EQ, these two things. And for both of them, you can also print out a message if that test fails. So then we see right here, there are things like expect true, expect false, expect EQ, expect any, and so on. The ones that we're interested in are expect EQ, and also related to expect any, expect LT, and so on. We wrote expect equal. So expect EQ is pretty much what we need. It's Google Test version of what we already had. What the expect functions do is they say if an error occurs, then print out an error message and then keep going with the rest of the code in that particular test. The assert functions are a little bit different. Assert EQ, if it reaches something and the two values that are passed into the function are not equal, then assert EQ says, okay, these two tests are not equal, I'm going to print it, or these two values are not equal, I'm going to print out a message, and then I'm going to crash. And the test case ends right there. That's where the program stops. Sometimes you want that, but in general, you don't want the program to stop immediately. You want to see all the different error messages that occur. So we're going to keep using expect EQ. Okay, that's pretty much all the information we need. Let's get started. We'll have to make a couple of changes. gtest.h. We'll have to include that file, which contains basically all of Google's code for Google Test. We won't be needing expect equal anymore, but I'll keep it there for now. Binary search, that's pretty much the same, it's pretty unchanged. Now these things over here, we have our three test functions: basic test, small vector test, empty vector test. We're going to have to rewrite these a little bit in a very particular format that's going to fit in. It's going to fit into the Google Test framework. I got all this information again from the README and from the primer. So if you're interested, then take a look at that afterward. But I'm just going to skip that for now and just show you exactly how it's supposed to be done. So you say the word test, test, and then the name of that test case. And the rest of that code is unchanged. I understand this is a little bit weird. I think some of you are saying, where's the return type? Isn't it supposed to be void? What does this weird capital test thing mean? Yeah, it's pretty weird, but you don't need to worry about it too much. Essentially, what's going on under the hood is that test, this capital T-E-S-T thing, is something called a macro. A macro in C++ is not exactly the same as a function, although it is a little bit similar. Essentially, we're actually invoking the preprocessor here. And what the preprocessor in C++ does, it says, okay, I'm going to take test. Whenever I see the word test in all caps, I'm going to substitute it with something else. And this is happening before your code is even compiled. When you say g++ -std equals whatever, and then binary search.cpp, that thing gets evaluated to something else, and then this becomes an actual function definition. And then it compiles your code. And that's why the syntax is a little bit strange. Google Test does this because it wants to do some stuff under the hood for its testing framework, and we're not really going to question it, we're just going to keep going with it. So this one is going to be kind of similar. All caps test. We're going to say binary search test, and then small vector test. The first word just indicates kind of, I think it's called the test suite. We can have a test suite, which we're calling a binary search test. And there are going to be multiple test functions, test cases, inside that giant test suite. So right now we have basic test and small vector test. We're also going to add empty vector test. Okay. We actually don't need these anymore. We don't need to call the tests ourselves. Google Test does that automatically for us. We just need to say, we need to take in the command line arguments and pass them into this weird function. Instead of returning 0, we return this value. Return run all tests. Again, I know this is really strange, but Google Test just says you have to do this. And you can look at the primer and the README online for more information. I think that's it. Let's see if it compiles. Actually, compiling this is going to be a little bit tricky because we need to specify where that file gtest/gtest.h actually is. Right now, the compiler doesn't know. Like if you try compiling it the way we did before, it's just going to give you that error. It says, yeah, I don't know what this file is, what are you doing? And the way to get around that is we need to pass in some more information to G++, the compiler. That tells us exactly where all the Google Test files are. This one is a little bit long. I'm going to write a script that actually does that for us. So I'm just going to write this thing over here. I'm going to write a bash script. If you don't know bash scripting, don't worry about it too much. I'm not really going to go too far in detail here. Essentially, everything that we type into this file is going to be run as if we were running it directly on the command line. So this is what we had before. We're going to make a couple of changes. First of all, we're going to create a variable in bash that stores the path to where the Google Test files are located. So that's where they are. I actually put them there so that we have access to them for things like the partial autograder for assignments and also for this discussion session now. Okay? We had to use it over here. So that directory /Google Test /Google Test again /include. You have to specify the pthread option because Google Test said so in their docs. And now we can specify all the files that we want to compile. Binary search.cpp, that one is obviously there, just like it was before. We have to specify one more though. And again, this is just there because Google Test needs it. I pretty much copied this command from the docs when I was writing the first version of the partial autograder, which was actually last semester for one of the assignments. And I've just been reusing that command pretty much ever since. Okay, that's the file. I just gave myself executable permission so that I can run the script. And let's see if it worked. Okay, if I didn't make any typos. All right, it worked. This is great. I was expecting there would be typos somewhere, but apparently there weren't. This is awesome. We still have the same binary as before, a.apt. That's the file containing all our compiled code, like with all the Google test stuff combined into it. And now we can just run that. If we run /a.app, we're going to see this output. I really hope this is familiar to all of you, because I've been using this for the partial autograders for the past several assignments. And yeah, it's essentially just saying Google test found 3 tests from the test suite binary search test that we defined in our file. Found basic test, that's one test case. It ran it and passed. Found small vector test, it ran that and passed. And then it found empty vector test, it ran that and passed. Does that make sense? What happened so far? We changed a bunch of code and now Google Test kind of did its magic and all our tests look really nice and there's all this information available to us. Okay? If you want to run only one of the tests instead of all of them, and again, this information, we have time. I'll actually look up the information this time. Okay, there's more stuff over here. We want it outside of this file. Okay, I'm going to go to the advanced Google test guide because I have even more information if you've read the README and the primer already. What we want to do is filter by test name. I think, yeah, that's it. Or maybe not that one. Yeah, here we go, running a subset of the tests. By default, the Google test program runs all the tests the user has defined, but we know this, we saw this already. Sometimes you want to run only a subset of the tests. And here are a couple of examples over here. So like you can say, run all the tests, or run everything using this format right here. You can say, run everything in that test suite binary search test that we defined, and so on. You don't have to use stars. Whenever you see star, that usually Google Test tries to expand that to all the different tests that match that particular name. So we basically saw we're supposed to say gtest underscore filter equals the test suite binary search test dot whatever test name you want to do. In this case, we're going to do, let's do the first one, basic test. I think that's what it's called. Yep, it ran only one. It gave a message over here, Google test filter equals binary search test on basic test. It ran the test and passed, and then it gave a little summary of all the tests that we ran, which in this case was just one. Okay, I'm going to go back to the code file. So far, everything looks pretty good. It seems like our binary search is working. It seems like we've come up with a nice testing framework. And it seems like those tests passed. There's one small issue in the binary search code itself, which we can fix right now. So yeah, believe it or not, there's actually a bug in this code. It's a very subtle bug, but it is there. Does anyone see it? Okay, probably not. Honestly, a couple of years ago, if you showed me this code over here, I would have said, yeah, this binary search, it looks perfect. In fact, most people would say, yeah, this is binary search, looks fine. But there actually is a bug here, and it's on this line right here. When we're saying the middle index is equal to the average of low and high that we were considering earlier. So we want to see what could go wrong with this line. I'm going to write another helper function. And it's going to take in two different numbers. And it's just going to return their average the way we're doing down here. And then over here, we're going to say, instead of getting the average directly, we're going to call our average function like that. The reason I want to make a separate function is so that we can start writing tests for it. So we're going to come up with more tests. And let's call this one average test. So what could possibly go wrong when you're saying n1 plus n2 over 2? So we can try saying things like, maybe you'll take the average of 0 and 0, and we expect that to be 0. If we take the average of 0 and 1, we expect that to be truncated, because that's what integer division does. It wouldn't really matter if it got truncated or rounded up, but we know that it's getting truncated right now, and that's perfectly fine for our purposes. So this behavior is fine. If we pass them in the other order, again, we're expecting that. 0. And I'll just write one more that I can think of. Maybe if two numbers are very far apart from each other. So the average of 0 and 10,000 should be 5,000. Okay, I'm going to save that. I'm going to run that script, compile test.sh. Oh man. Okay, I know what I did. Okay, line 22. Instead of n1 and n2, which should have been low and high. There we go. Now we'll compile. And we'll run all the tests. We want to see all of them. Okay, these are still passing. It seems like we haven't hit any issues yet. What if we're taking the average of two numbers that are very large? All right, let's see. Ah man, let me try that again. 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. It should work for large numbers too, right? That makes sense. Hopefully I typed those right. Those are all be 2 billion. Compile tests, and then do this. And now we see a failure. It says expected the average, or expected average, which is this thing, to be equal to 2 billion. So we did something wrong here. So there actually is a bug in our average function, which only seems to happen for really large numbers. I'm not sure how much of a background any of you have in things like the sizes of integers on some different architectures, but basically integers are 32-bit numbers, which means they can store values from -2 to the 31 up to about 2 to the 31. So 2 billion is in that range, but the sum of 2 billion with itself is not in that range. It actually overflows, and it gave us some weird negative number. So saying n1 plus n2 can actually cause integer overflow, which is bad. And the way to fix that is to say something more like this. We take n1, and then we take half of the difference between the two numbers. And I believe that should work. Okay, apparently not. And plus whatever. I don't think that changes anything actually. Okay, it seems like there's a typo in my notes. I guess you have to say the minimum of them plus the larger minus the lesser divided by 2. That's actually how it would be, which would be a little bit longer than what we have over here. Okay. I'm going a little bit over. I need to return some of my equipment. So in the interest of time, I'm going to stop here. That's pretty much all I have to say for testing. Yeah, so if you're interested in testing, I actually recommend the first approach that I used, which is writing a bunch of assert statements or writing a bunch of warnings like that. The expect equal function at the top. Like for your code, if you're working on assignments, that's actually probably the easiest thing to do. It's easier than trying to get Google tests involved. But for the project, if you want to get Google tests involved, then that might be a good idea. It might be useful to write some more advanced test cases. Because obviously for your projects, we're not going to be providing test cases for you. Yeah, if you're ever interested in that, if you ever want help with that, then just talk to me. Yeah, talk to me. I don't know if Isaac knows how to use Google Test. And then if you come to my office hours to set up an appointment, I can help you with that. Okay, thanks for coming.